Hello and welcome to Inside the Logic, real talk with FPGA engineers. I am your host, Kevin Rosenquist, and today we're diving into FPGAs and why they aren't just surviving, but they're thriving. They're the reprogrammable powerhouses behind everything from satellites to EVs. And joining me today, we've got Charles Sobczak and Ryan Erickson, and we're going to explore what makes FPGAs unique, where they're showing up in today's tech, and why the next generation of engineers should care. Ryan, Charles, good to see you guys.
Good to see you, Kevin.
Good to see you. Thanks for having us.
Absolutely. So tell me what makes FPGAs unique versus, say, CPUs, GPUs, or the like?
Yeah, so the way I usually try and explain it is, well, starting with an ASIC. ASIC is sort of the smallest building block with which you could really design any algorithm or any piece of physical hardware. So it's kind of like a single Lego block. If you're thinking of Legos, most everybody knows what Legos are. So it's like a 1x1 Lego block. And then FPGAs are like the closest to that. So it's the next size building block where, say, it's like a 2x2 Lego, like, four little blocks that you can put on top of one another. Now with the ASIC, you're basically gluing it down. So whatever you design, you're going to be stuck with. So the second thing that we kind of do is we kind of zoom out and then we talk about sort of the benefits and the trade-offs between FPGAs and the other devices. And so if we go from CPU to GPU to FPGA to ASICs, sort of it's a bit of an oversimplification, but as we go from CPU to FPGAs to ASICs, the device is more parallel. And what that means is that you can run multiple operations at the same time. So whereas a CPU, if you want to do a multiplication or some sort of mathematical operation, it may take 7 steps before you can actually even do that operation.
Mm-hmm.
Now, an FPGA, if you have enough resources for that mathematical operation, it all happens in one step. So parallelism, that's the first part, the real benefit of an FPGA. The second benefit that I think is more and more the spotlight is getting shined on, and that is the low latency aspect. If you design it carefully, you can make it so that the time between an input, you're detecting or estimating something, and you create an action, that amount of time is very, very small in FPGAs and ASICs. So then there's two sort of limitations with an FPGA, and that is that the time to market is a little bit longer. You need a team of specialized skill sets. They need to know a programming language called Verilog, and Verilog is a very low-level programming language. So to really optimally design it, you need to be thinking at these low levels of gates. And not only that, but you need to be thinking about, instead of like a software engineer maybe thinking in floats or doubles, we're thinking in actual bits to optimize it. So if we're dealing with an RGB, each are like red, green, blue, they could each be 8 bits. It'd be more optimal to do the mathematical operations like on 8 bits. So time to market is a bit of a challenge for FPGAs. And then like I was alluding to, the last part is that the skill set is, for an FPGA team, you really do need a wider breadth of skill set. You may need signal processing engineers who are dealing with the algorithms, the FPGA engineers who are implementing that algorithm on the fabric, and then software engineers, and maybe even a hardware engineer to design the board. And then I guess lastly, this kind of sews into what we are as a team for FPGA Workbench. But we recognize those challenges, the benefits, parallelism and low latency, and there are other benefits as well, lower power on average, and then recognizing the challenges, which is the time to market, and then you really need an FPGA engineer. And so we created mission statements around our product to sort of identify those. So the two really mission statements of FPGA Workbench, the first is to lower the barrier to entry for customers who want to have that FPGA solution, the low latency and the parallelism, but they don't maybe have that skill set on their team. So that's number one. And then the second one, because we are not necessarily like the end product, we're currently right now more in simulations. We, instead of saying time to market, we say from idea to bench testing. So our product tries to identify those things, sort of integrating a graphical test bench with the FPGA card, with the software development kit, with the drivers. So that kind of gives you a high level view about the devices and kind of the benefits of what we're doing.
You mentioned the math problem maybe taking 7 steps, but can you give me an example of a problem where you feel only an FPGA would work well?
So there's always trade-offs. So it's sort of a more optimal solution. So an FPGA is going to give you a more optimal solution for something that you really need super low latency. It's almost always going to be better in that case. So if you and this kind of segues into signal processing, my area of love, which signal processing is about detecting, estimating, and classifying things. And then also in action. The most easy way to explain it is like visually. So let's say you're looking at the blue canvas of the sky and you see an object that's moving in the sky. The first thing you do is you're going to detect, hey, there's an object in that blue pixelated canvas of the sky. The second step is you're going to estimate some parameters of that object. So you're going to estimate maybe the size or the shape, and then the first and second derivatives, so velocity and acceleration. So you're going to estimate properties of that, and then you're going to classify it. Was it a bird? Was it an airplane? Is it a friend? Is it a foe? And then you need to take an action. So in that sort of algorithmic flow, what's really important and becoming more and more important today is that low latency. You need to be able to detect quickly, estimate, classify, and create an action more and more quickly. Because what we see is that we're moving towards a world in some sense where the
Mhm.
human is removed from the loop. So as the human's removed from the loop, which is a lot slower, and computers and algorithms are running, you need the algorithm to be running on the edge. So FPGAs are really well oriented towards doing that algorithm on the edge, and detecting, estimating, classifying is one of them in the world of signal processing.
Where are you guys seeing FPGAs used more and more today, and what industries are they kind of gaining momentum?
Yeah, that's a great question. Traditionally, newer technologies start in government. And if we roll back 20 years ago, FPGAs were primarily in sort of in the government sector. And over the years, we've seen it move from government to aerospace and automotive, and it's pretty much used everywhere. Now, the super high tech stuff is still in the government sector, and it's again kind of a little more focusing on compute at the edge. So edge compute rather than cloud compute, or there is some aspects where it's used in cloud compute, but GPUs kind of have that locked down. So really, that sort of idea of really at the edge compute.
What do you think is driving the demand for using FPGAs more and more?
It's twofold. One, the benefits of reconfiguring the algorithm. So there was a lot of efforts on something called software definable radio, and I worked a lot of that in my last company where we're working in the government. And in that case, it's you need a device that is very well programmable, targeting a solution, but you need to be able to reprogram it for certain features. So I think that's kind of
Mhm.
the benefit. So if we talked about parallelism is obviously a huge benefit. The fact that you can reconfigure the algorithm, and I think as we go forward, and I know we'll probably talk about it later in terms of AI and ML, AI inference and machine learning, the ability to reprogram aspects of it on the fly for a targeted application are going to really show some benefits as we go forward for those edge solutions.
So Charles, I can definitely sense why you love FPGAs, why you care, why you're into this whole thing. Why should new engineers care about this technology? Why would, for someone just coming up in the computing world, like getting out of college, whatever, what would you say is the main reason that they really need to be paying attention?
Yes, at first, like you said, they're just very cool, and they're cool. They're awesome because if you want to, I mean, I think if you want to be able to implement an algorithm, and you want to be able to implement the algorithm that is functioning like at the tip of the spear at the edge, which is there's a lot of similarities between that and kind of the way, like the example of detecting an object in the sky. It's There's a lot of similarities between the way humans navigate the world. It's the way we detect, estimate, and classify things. And so if you like to do algorithms and you have a very complicated algorithm that you want to implement, then FPGAs are one of the primary solutions for that.
Okay. Are they difficult to learn? What's the learning curve like on these? Not that I'm saying I'm going to figure it
Yeah.
out, but like for someone who actually knows something about this stuff.
Yeah, so I mean, it definitely there's a large learning curve, and the skill sets required to be an FPGA engineer require learning this language called Verilog or VHDL, and it is a very low level language where programming a CPU or a GPU is a much higher level language. So you don't need to know as much of the details of the physical architecture and the actual logic blocks. So it's challenging, but I think with anything, usually, often, the harder something is, the more rewards, the better it is, right? So if it's something
Yeah.
challenging to go through, you usually are better for it. And so I guess that's kind of my perspective. I don't know if Ryan wants to add something about that as well.
I mean, yeah, truthfully, FPGA, learning how to do FPGA design, it is not easy. It takes a lot of love. You have to actually want to do it. But it boils down to an art form, truthfully, because FPGAs themselves, it's a reprogrammable canvas of the basic building blocks of computer architecture. And, ASICs might be able to do things slightly faster or just as good as FPGAs, but the reprogrammability allows for a lot more expression and thought in creating these algorithms that can update in real time, these changes you can make, because there's something about an FPGA giving the opportunity to make a change. Because like for an ASIC, anything that can be done on an FPGA can be done on an ASIC for sure, except once it's placed, and that can never change. And so there is beauty and, frankly, skill expression when learning how to do FPGA design, where you allow for change to be made in the future. Maybe you leave hooks in something for something to be changed. Maybe you design an algorithm that is specifically meant to be changed, or maybe it's supposed to update and learn. And so it really boils down to, it's like an art form like drawing or painting. You learn the basic building blocks of how to create this picture. I fully invest and fully buy into the idea of FPGA design. It takes a lot to learn it. It takes a lot of time and dedication, but it's 100% worth it. And like Charles said, the rewards for the difficulty are definitely there.
Awesome. Well, that's really super interesting stuff. Thank you all for joining us on Inside the Logic, real talk with FPGA engineers. Thank you very much, Charles Sobczak and Ryan Erickson. Excited to keep going. We got more episodes coming. I'm excited to learn more about these FPGAs. It's really impressive technology and exciting. Thank you both for being here.
Thank you, Kevin.
Yeah, thank you for having us.